Yeah, so our next talk, we're very happy to have Francois Dahmani, who will tell us about the normal closure of a big Dehn twist in a mapping class group.
Thank you, and I would like to thank the organizers also. Let me start with the setup for this talk. Sigma will be closed oriented. Oh, yes. Thank you. Thank you again. You will hear me better? No? Yeah. Good. Sigma will be a closed orientable surface of genus more than 2. The mapping class group of sigma will be the mapping class group of sigma. Okay. But you know what? Alpha will be a simple closed curve. On sigma. And we are interested in the question, oh, yes, tau, let's say tau alpha will be the Dehn twist, the simple Dehn twist on alpha. Over alpha, around alpha, I don't know. And it is an element of the mapping class group of sigma. Well, I see it as an element of the mapping class group of sigma. So it's usual, realized by the usual diffeomorphism that you have your surface somewhere. Okay, somewhere you have this curve alpha. It can be separating or not separating, I don't care. You cut a little neighborhood cylinder around alpha. Well, I don't know why you have put it red. It's unnecessary use of color. So this is alpha. This is a little neighborhood of alpha. You are the identity on both sides, and inside this little cylinder, you make a full twist in one direction, whatever you choose, and this is called tau alpha. So the question is, what does the normal closure of tau alpha look like in mapping class group? But that's not a very interesting question asked like that. I don't think so. If you pass, and we will see why it's interesting to talk about this. If we pass to a power of tau alpha, what is the normal closure in the mapping class group of tau alpha to the power n? Say. So what is the normal closure of tau alpha of, say, the power n in the mapping class group of sigma?
More interesting, isn't it?
I'm sorry?
More interesting.
That's more interesting. I suppose so. Yeah. Okay. For large n. So a little bit of background for this kind of question. Let me frame it because it's already not well aligned. But anyway, a little bit of of background for this question. We would like to know what are the normal subgroups of the mapping class groups. What do they look like? The first time I heard about this kind of questions is in in the book of, well, I don't remember. It was from Farb and or Ivanov. They would ask, what is the normal closure of a high power of a pseudo-nodes of element? So, but it was said that as a test question. So can we understand a little bit better the normal subgroups of mapping class group? I think I'm not completely sure that behind these questions. Okay, so we understand some of normal subgroups of mapping class groups, as a Torelli group, Torelli subgroup, and this kind of thing. But I think that behind these questions was the correspondence or the analogy between mapping class groups on one side and lattices of simple Lie groups on the other side. And okay, so we know more about normal subgroups of lattices, of higher rank lattices, say. And so what can be said for this analogy in this topic? Yeah, so if I draw a little bit more on that trend, so there is an analogy, mapping class group lattices. Okay, it comes from the maybe SL and Z. I don't know why I'm talking about complicated stuff. SL and Z, maybe. So this is why is that? Very naively, it's easy to explain. GL and Z okay, is the automorphism group of free abelian groups, Z to the n. Mapping class group is the automorphism group of surface groups. So you have on one side Euclidean lattice and their automorphism, on the other side hyperbolic lattice and their automorphisms. So first, it's a good start for this analogy, and a lot of things were done in this trend. So that's only my guess. I don't know if it's completely true. Maybe you can correct me. This question was maybe motivated by this kind of thing. Okay, and in this analogy, you have some rank 1, so corresponding to SL2, and maybe some things that looks more like higher rank corresponding to SLn for larger n. So there are the areas of the mapping class groups where there are the pseudo-nodes of elements. So that would be rank 1. And they are the rest of the mapping class group, consisting of reducible elements. That would be in the analogy with higher rank. So n is not very well defined here. Okay, and so first, this question was a normal closure of something of rank 1, like something that exhibits some hyperbolic geometry. I'll come back to that in a minute. You can expect that this will behave as in SL2 or as in hyperbolic geometry setting, so that you have a normal closure that is not too big, and that's what's happening. So in collaboration with Girardel and Ossine, we say that there exists n. So given sigma, there exists n such that for all pseudo-nodes of element gamma in mapping class group of sigma. Yes. Well, let me say that like that. The normal closure of gamma to the n, or actually, there exists for sufficiently large n in the mapping class group of n prime of. So, did I get that correctly? For all n prime larger than n, normal closure. Did I get that correctly? Okay. Of gamma to the n prime in the mapping class group is free and purely pseudo-Anosov.
And your first n depends presumably on the genus, but nothing else.
That's right. It depends on sigma. Right. Yeah. N0, N sigma, N0. Let me say it that way. So free, it's a normal closure, so it's generated by all the conjugates of this gamma to the n prime. It's free, but it's infinitely generated. Okay, so it's not everything. It's far from being everything. You can say even something about the quotient. The quotient is still nice, big, whatever. So it's really much in the line of rank 1 hyperbolic setting or whatever. Okay, so maybe we expect something different for reducible elements. Because we expect something in the line of the higher rank. Okay, maybe toward a guess, I should say, still on the background on this question, or slightly over it, a result of Koberda is whenever you take a family of simple closed curve, a finite family, given any finite family of simple closed curve, alpha 1, alpha k, there exists n 1 such that the group, only the group, generated by tau alpha 1 to the n1, tau alpha k to the n1, this group is a right-angled Artin group. With a natural presentation of a right-angled Artin group. What do I mean by that? So right-angled Artin group means you have a family of generators and relations that some selected pairs of these generators commute. And that's it. So here is a family of generators. And the selection that some of them should commute is simply when you have two Dehn twists over disjoint curves. Well, in this picture, you can see that they commute because their support are disjoint. With a natural right angle Artin group presentation structure, I should say, probably. Dehn twist over disjoint curves commute. Okay. If you want to play this game with Pseudo-Nosov, so it's a difficult theorem. So if you want to play this game with Pseudo-Nosov, it's easier because it's a ping-pong thing, and you will end with this finitely generated group to be free if the Pseudo-Nosovs are independent. I should have said distinct curves. If you use twice the same curve, that's cheating, right? Okay. Anyway. Okay. So what's the guess for the normal closure of the Dehn twist, of a Dehn twist? So guess. You have a guess? Anyone guess? For
The right-angled arcing group on the one skeleton of the curve complex.
Thank you. No. No. So I thought that too for a while. I even thought what I was doing was a proof of that, except for those technical details that will eventually work. Then I learned that Dan Margalit and Tara Brendel and Dan Margalit have proved a very convenient theorem for me, is that if you have a normal subgroup, so it fits a little bit in the higher rank analogy, I suppose. I'm not completely confident with that. If you have a normal subgroup of the mapping class group that contains an element with small support, and well, this thing is definitely an example. It is the example, I suppose. Then its automorphism group is essentially the mapping class group itself, acting by conjugation. But in the right-angle arcing group, you have automorphisms that cannot come from that. For instance, you send one of the generators to its inverse, and that's it. The other ones are still the same. That's an automorphism, because on the presentation of a right-angle arcing group, I didn't write what was a right-angle arcing group. Should I write it here? What do I mean precisely by right-angle arcing group? Yes, no. If you scream no, I don't. So you don't scream no, so I do. Okay. So yeah, so in a presentation of a right-angle arcing group, you can just flip one element. So that means that you're suddenly taking the inverse of a Dehn twist, but not of all the others, not of all those ones that cross this curve. It cannot come from a diffeomorphism of the surface. It's just an abstract algebraic automorphism. So it cannot be. It doesn't fit in that.
Can you say the exact statement of the theorem of Brendel?
I can say consequence. I will not say the exact sequence. The consequence that such a group, its automorphism group would be the extended mapping class group. Yes. Out of. I think the extended. No, I don't. Yeah. The extended meaning you can reverse orientation, listen for the whole surface. Okay, so no. So what is okay, another guess could have been, it's the whole group. Well, no, neither. Because, and this again, I'm sorry, I'm not familiar with almost nothing in that thing. With something with which I'm not familiar neither, you know that you have so-called quantum linear representation of the mapping class group. Some of them are such that the image of all Dehn twists is for finite order. But they still have infinite image. And I cannot comment on that. So what's the result? Statement, so theorem, say. So there exists n0 such that for all n larger than n0, what do I want? Okay, the normal closure of tau alpha to the n. Sorry, I did not reintroduce the notations. That's something you can do in a statement of a theorem, but it's written on the left. In the mapping class group, has a partially commutative presentation over some selection of conjugates of tau alpha. So what does it mean? Tau alpha to the n. So what does it mean? So more precisely, there exists S, a collection of conjugates of tau alpha, such that and there exists R, so that's my generating set, that would be my relators, and R are a set of relators of the form the commutator of S with GS G inverse, where G is a word. No, wait, S prime. Yes, the commutator of S and G, S prime, G inverse, where G is a word in S, and S and S prime are in S. And such that, well, my group, tau alpha to the n mapping class group, the closure in the mapping class group of tau alpha to the n is isomorphic to S R. And I should say in a natural way, meaning that the isomorphism really sends the element S to what it is really. It's not, yes?
Is the presentation stable under taking larger n?
Yes, actually, that's the presentation is okay.
It depends on n naught only, not on n. The presentation only depends on, well, is once and for all and not depends on n.
So first, you have a choice here. You can choose specific collections of conjugates. Once you've done this choice, the relators are the one, the naive one. That means the two guys that can, one of them can be expressed as a conjugate of some element is S, but commute if and only if they are disjoint. So in that sense, it does not depend on n.
Sorry, how are we talking about disjointness? How does G affect what you meant to say about disjointness?
Okay, so S is a conjugate of tau alpha, so it's a Dehn twist around a certain curve. S prime also, it's a Dehn twist around another curve. And GS prime G inverse is another conjugate, so it's a Dehn twist over a third curve. So the criterion is that the first curve and the third curve are disjoint.
And that third curve is G of the second curve.
That is right. That's yes, or G inverse. Or acting on the right or on the left. But the point is that maybe this conjugate is not in the family S. And this happens already, so I don't want to sidetrack so much, but this happens already here. This group for mapping for pseudo-Anosov is free, but the basis for which it is free is a certain collection of the conjugates of gamma to the n prime, and not all of them. Not all of them. You have too many. If you take all of them, it's no longer free. You have a relation saying, actually, this one was the conjugate of that one by that one. So that's okay. So that's what's happening here also. If you want some minimal generating sets, in some sense, you have to select some conjugates, not all. If you want to take all the conjugates as a generating set, then you have new relations that say, okay, but that guy was the conjugate of this one by that one. That's new relations. I don't, yeah. I prefer this formulation because here we see that all the relations are in the derived subgroup. So it's better to see, for instance, that it's not everything.
And S is an infinite set, presumably.
And S is infinite. I don't know where to write that. The observation or comment. S will be infinite. R is the natural commutation relations. So this disjointness of curves. And I forgot what was the third comment that I wanted to do. So in some sense it's satisfying, or to me it's satisfying because it says there are no exotic relations. There are no relations that you don't expect from the most simple naive observation of the picture, if you take sufficiently big Dehn twists. Okay. I should go to the method of the proof. Yes. I thought I had something more to say. No, I forgot. Okay, I forgot. So the method is an adaptation of the method that was used here for the pseudo-Anosov elements. So maybe I will try to first sketch what was the method for the pseudo-Anosov case. Okay. So this uses the so-called tool of rotating families. I will, okay. So what's the setup in that case? I will forget a little bit that I'm talking about mapping class group. I will just draw a more abstract setup. So notations are changing a little bit, but so you have a group G acting on a hyperbolic space X by isometries. X is maybe geodesic. And you have gamma in G that is loxodromic in X, that is there's an axis in X. And that has an interesting property. That is called weakly proper discontinuity, WWPD for the experts. What that say? What does it? What is it say? Okay. What is it? So. Okay. Well, why do I draw a hyperbolic space? I will only draw what is interesting. It would be better. So in X, being loxodromic means you have a translation axis. You move by translation on this axis, and everything else is more or less controlled by what's happening by projection. But of course, it can be very more or less controlled. Okay, axis of gamma. Okay, let me write that. Okay. Now we are interested in the group generated by not only by gamma but all its conjugates. So I want to look at a conjugate of gamma. Well, it's still loxodromic. It has an axis. If it's conjugated by G, its axis is now the image of A gamma by the isometry G. So let me draw it like that. Maybe. And maybe I have a third axis somewhere else. I don't know. What could be interesting? Maybe I have a third axis somewhere else that looks like that. So A of H gamma H inverse. So the property I want is about the overlapping of the different axes of conjugates. And I want that two different axes do not overlap by more than a certain uniform constant. I don't want to see more and more overlapping as I conjugate by more and more elements. So, axis of conjugates are equal, this I accept, or I don't know, there are many terms for that. Mutually co-bounded, do you accept that? Or have small projection to one another, are delta mutually co-bounded. Maybe it's a strange formulation, I don't know, meaning that do not overlap more than delta. Okay, so this is the two assumptions on my action, in addition of the hyperbolicity here. Okay.
When you say conjugate axes are equal, do you mean also parallel in there?
Yeah, well, quasi-axis, axis, I was avoiding that.
So, and when you mean overlap, you mean delta overlap?
That's right.
Okay.
That's right. Yeah. No, do not, I don't know, 20 delta overlap. There is. It depends on their quasi-geodesicity constant. The one thing I want to avoid now is constants. So there are ways to avoid it, but okay. Oh, well, I hope the picture is okay. Okay, so what do you do when you have that? Well, you can do this rotating family's machinery. I will sketch it very briefly, so it's no detail. So there are several steps to analyze the structure of the normal subgroup you're after. So the first step is to cone off those axes. By large cones, large hyperbolic cones, cones that are even cut, locally modeled in the hyperbolic plane. You can do that. So the picture would be like that. So you have. So now they do not overlap much, and you adding some big cone points and an angular sector. You can think of it, if you had really lines, you can think of it very concretely by taking an angular sector in the hyperbolic plane or in the ramified cover of the hyperbolic plane of infinite angle. So in other words, you take your favorite angular sector in the hyperbolic plane. Here it is. It has a certain angle here. It has radius r0. Here is an arc of circle. You take plenty of it. You glue them on their side, left and right. Then you have an infinite line as a boundary of your infinite cone of infinite angle at this apex. And you glue this line on the axis. That's what I do as cone off. So this really is smooth version of a cone, not a strong one for which you destroy everything by diameter 1 or so. Here R0 is big. We will see why in 2 minutes. Two, what is two? This defines what is called the rotating family. So it's a concept due to Grenoble in the Cat 0 setting originally, but that has been improved by many people now. And so what is it? So now in this new space that was the axis of the loxodromic element now are coned off. If it's done in an equivariant way, you still have the G action on this cone off space. The translation along the axis are now rotations along, over the apices. Instead of translating by this distance, you are rotating by this angle. Okay. And if you take a sufficiently strong pseudo-Anosov or a high power of pseudo-Anosov, what happens is that this angle is larger than 2 pi. And this will play a role. That's what it is, a rotating family. It's a collection of rotation in a space, which is invariant under the group action, a collection of rotation subgroups. Equivariant for G. And there are technical assumptions. So the apices for the rotation have to be far from one another. The angles of rotation have to be bigger than 2 pi. And what do you do with that? Well, there is this implies, and I will sketch why, how to analyze the structure. This implies that the group generated by all those rotations, which is the normal subgroup generated by one of them, is free. And I will try to sketch now this implication. And the rest of the time will be what are the spaces we would like to use for this theorem, what is going wrong, and how to fix that. Maybe. So how do you get a free group? To get a free group, you need trees. You need a tree in principle. And this will be achieved kind of stratum by stratum, so you will have several trees. So what's happening in this picture, argument due to Gromov and adapted by DGO in the case we need. So let's start with one of the apices of the rotation. So you have a space. Now the space is x dot. Oh, it's green. The cone of space obtained from x. In x dot, you have those cone points. Around which you have a rotation group. Each time you have a cone point correspond to coning an axis. You have this, what was the translation, now it's a rotation. Start with one of them, okay. And have a little ball around it. For the moment, it's just a ball around the cone point. It's invariant under the rotation of this cone point. So call it A, this cone point, and call the rotation, well, rho of A. This ball is invariant under rho of A. Nothing fancy here. Now let the ball grow. I draw a little more cone points to have the thing. Let the ball grow. It's still invariant under the rotation it contains, no problem. Then it approaches some new rotation point. If I continue to grow, it will not be invariant under the rotation it contains because of those new rotations. So I have to incorporate them. No problem. Joined by a little arc or by geodesics or whatever. And look at what this rotation, it's rho b, what it does. It rotates by a large angle. So I'm drawing a few of the iterates of rho b, of the image of this ball, that for some reason I want to call W. So this is rho b of W, rho b square of W, etc. But I don't stop here because it's not invariant under rho A now, so I continue. Now I have the image of rho A of the apex A, and the image of the apex B by the rotations around those blobs. And if I unfold by the whole group generated by rho A and rho B, I see some pieces of blobs going around. I want to prove that those pieces have a structure of tree. And that would mean that now my group is not only rho A, is the group in which leaves a picture invariant is rho A star rho B, the free product. And then I will go on, and I have continuously, I will have several times a new free product attaching to the rest. That's how we get the free structure. I have 1 minute, because I need some time for the rest, to explain why it is a tree. Why is it a tree, this picture? Because it goes very far. Huh? Okay, sorry. In principle, it could make a big loop or something. Okay, take 1 point in one of the, in W, and 1 point in one of the image of W. So this is in, I don't know, H of W. I have one candidate for a path between that one and that one. And the candidate is to follow the pieces that were unfolded. this patch HW is obtained by turning around B, then turning around the image of A, then turning around something else. It gives me a sequence of rotations that arrives to HW. So it gives me a candidate of path. And I claim that this candidate of path is actually a quasi-geodesic. Why is that? Well, each time it travels inside one of the images of W, because it's a ball, it's quasi-convex. So this is locally a geodesic or a quasi-geodesic. Each time it travels around a rotation point, let me go back here. Each time it travels in a rotation point, it travels through something for which the angle is large. Well, what does it mean that the angle is large? It means that you have no shortcut between this point and this point. If you had one, well, the angle would not be 2 pi. From this point to this point, every geodesic has to go through this conical singularity. So, in the end, what I know here is that when it travels an image of W, it's a quasi-geodesic. When it travels a cone point, it's a quasi-geodesic. So it's a local quasi-geodesic everywhere. And because the space is hyperbolic, it's a global quasi-geodesic. So my candidate is a global quasi-geodesic, so it estimates the distance between that point and that point. I cannot have moved back to my original point. It's a tree. We have the free product. We're happy, and that's how it works. Okay. Now I have 7 minutes to explain why it doesn't work and why it works in our setting. So, oh yeah, for pseudo-Anosov elements, we use this technology on the curve complex, on which pseudo-Anosov elements are loxodromic, and the action is acylindrical, so we have everything. But what about Dehn twists? Then there is another important ingredient. It's the work of Bezvina, Bromberg, and Fujiwara. So what about Dehn twist? So Bezvina, Bromberg, and Fujiwara prove the following theorem. So I come back to the mapping class group. I take back the notations that I just erased, but you remember them. So they say the following. There exists a finite index subgroup G0, and you can take it normal, so in the mapping class group of sigma, and there exists a finite coloring of the set of simple closed curves in sigma that is G0 invariant. And that has a property, technical but I stated because it's short, that if two curves have the same color, they intersect. And that's a very nice observation, but it has some consequences. Because in their work, they develop a transition between an axiomatization of what it means to have a projection system to the construction of actual spaces for which the projection system is realized. I won't go through these details because I'm lacking. So I think that Mark will show me this these banners very soon. So. So what do they use that for? They use that for to construct quasi-trees on which the G0 acts. And so theorem of BF. There exists a finite collection of quasi-trees. So hyperbolic space is quasi-isometric to trees on which G0 acts and on which every Dehn twist. Okay, I should call them T1, Tm, or no, Qt1, Qtm. Every Dehn twist is loxodromic on one of them and elliptic on the other. So, yeah, I thought I would have been able to discuss more the relation between that and that. So now it's kind of awkward to have the first statement, I suppose. It's really quasi-trees made of arc complexes for the annuli of the curves, and there are as many quasi-trees than colors. Could say that, yes. And then, so what's happening? Oh, and also, they are loxodromic with this property on the axis. Plus, I did not give name. Property, so mutual co-boundedness. So that looks good in the sense that if m equals to 1, I have a quasi-tree on which the Dehn twists are loxodromic and have nice axes. And, so that's not what I wanted to say. Sorry. That's not what I wanted to say. That looks good because, take it back, consider alpha. And it has a quasi-tree on which the Dehn twist of alpha is loxodromic. Say its quasi-tree is number 1. So you can run the same argument. And what you get, so Coro, that the normal closure of tau alpha to the n in G0 is 3. Thank you. But that's not what you want. That's not what you wanted. You don't want 3. You want to see some commutation. And you don't want G0. That's the problem. You want the mapping class group. So that's not the good answer to the good question. That's a good answer, but to a bad question. So the question is tau alpha, and obviously I won't have time to develop more about what's the critical point that makes it work in G0, in mapping class group. It is the same as the normal closure in G0 of some conjugate tau alpha, tau G1 alpha to Gm alpha, where G1, Gm is the transversal for G0 in mapping class group. That's purely general nonsense. And each of them get a nice action on one of the coordinates. So all the story will be, or will not, well, should have been, to perform the argument of the rotating families simultaneously on each of the quasi-trees. And I just sketch one thing that can go wrong, and that I suppose in generality does go wrong, and say one word of why it doesn't go wrong. So run argument, so rotating families argument simultaneously on all quasi-trees. So what can go wrong? Just, okay, still have some seconds here. When I'm doing the rotation here, because the rotation is large in this space, I'm obtaining a tree in the on which the group I want to analyze act, the brown tree, the red tree. Is it red? I'm obtaining a tree because of the large rotation. But when I'm doing the exact same transformation on the other coordinates, I'm not using large rotations. So in the other coordinates, maybe I had some quasi-convex subset that was used to analyze the first stratum of my group. And then I'm doing a rotation on which I don't know anything. So I'm doing not only once, you saw, I'm doing all the groups. So I have plenty of images of this blob. Can be highly non-quasi-convex, I suppose. It can cover everything, or more or less everything. So it's not suitable for performing the argument. You need some tool to control what is the image in the what I call the secondary rotations. So when you're doing a rotation by some of the Dehn twist, but when you're looking at it on a quasi-tree in which it's elliptic. It's elliptic but non-trivial. So you need something, and this something is actually inside the technology from there to there. It is using the projection systems, the subsurface projection in the mapping class group, and the improvement of Bazimida Bombay Fujiwara. And it is using the so-called Berstock inequality, which I have over time to discuss. But with the inside technology here, you can show that in the secondary coordinates, meaning that not the coordinates of the large rotation, but doing the same element, but in a quasi-tree in which it, in principle, it does not belong. Well, you have something messy, but the projection on any cone remains bounded. And that's the only thing you need to continue the argument. So I was over time. I'm so sorry. Thank you for your attention.
Do you have any questions?
Did I understand you rightly that the Brendel-Marguerite theorem tells you that your group not just isn't the obvious right-angled Darton group, but isn't a right-angled Darton group at all?
That's right. Yeah.
Anyone else? Thank you, Francois.